Okay, so we're all here. Okay. Okay, so today we'll continue with the Tobit model. So after the topics on the first exam, we've been focusing on limited dependent variable models. Um, we started with the basic binary response models, the probit, um, logit model, and then we went to the um, more general multinomial and ordered response models. So for unordered responses, we had the multinomial logit and the conditional logit. Okay. And then for the ordered response models, we have the ordered probit. And similarly, you can get the ordered logit model. Um, So note that the choice of model you would be using here depends on the characteristics of the left-hand side variable. Okay, the dependent variable. Um, then for corner solutions, we have the Tobit model. For the Tobit model, the zeros that you observe are outcomes of um, the behavior of the economic agent. Okay, so it's not really a data problem, but it's simply um, how you measure the response of the economic agent. Okay. Okay, so let's continue um, with the Tobit model. Okay, I will upload the Charles upload the files today. Okay, so I will upload an updated file on the Tobit models. I just corrected some of the subscripts. The excess, I forgot to put an I for some of those excess. And then I will upload lecture 8, which is on sensor data. Okay, okay, so I'll move to share screen. Oh, okay. Well, I'll go to chat first and upload the files. Um, okay, so I have uploaded the two files. Um, okay, I'll move on to share screen. Okay, so we're into the Tobit models. We have started with the type 1 Tobit model. Then we'll finish the two limit Tobit model. Okay. So, I'll just see where I ended up. Um, okay, so we'll go to um, treatment effects. Okay. Okay. So as I mentioned before, the partial effects of the average, um, at the average, the average partial effect. Okay. So here, um, this should have a subscript. Okay, so the partial effect of the average you evaluate at x bar. The average partial effect, um, no, this is right because you would consider that for all x's because you're getting the average. So there really should be no subscript. Okay, okay. So note that for the partial effects, um, the partial effects are not directly given by the coefficients, but you have scaling factors. Okay, the scaling factors being some numbers between 0 and 1. Okay, let's move on to the average treatment effect. For the partial effect of the average and the average partial effect, note that we are getting partial derivatives. So here we are assuming that the x of j's are continuous. Okay. For the average treatment effects, um, we have looking at the effects when we have the x's are binary, when the particular x is a binary variable, or when you have large changes for the continuous variables. Okay. Since when you're getting derivatives, you are looking at the marginal effect. So if you have large changes, then the derivatives are not valid to um, estimate the changes. Okay. Okay. For the average treatment effect, okay, um, we calculate those for discrete explanatory variables or for large changes in the continuous variables. That is for the right-hand side variable. Okay, so we compute the difference in this expected value of y given x at different values of x. Okay. Okay, so we've gotten the expected value of y given x. Okay. We have here the expected value of y given x. I think we have a more, okay. So this, for expected value of y given x, this is for the type 1 two-bit model where we have zeros and positive values of y, okay? So the expected value of y given x is given by this expression, okay? So here we have to evaluate the CDF at x beta over sigma and the density function at x beta over sigma. Okay. Well, the computer can easily do that. Okay, so this is, so you have to calculate the, for large changes, suppose x goes from x of 1 to x of 2, then you have to evaluate this expected value at x of 1 and at x of 2 and get the difference. Okay. So let us see if the x is a discrete random variable. So we get the average treatment effect. Okay. Okay, so suppose we reorder the x's such that the last variable is a binary variable, such as a policy indicator. So x of k can be 0 or 1, 0 if you have no treatment, 1 if you have treatment. Okay. And define for each observation I the following indices. Okay. Therefore, if you have the treatment, then you would have w sub I1 hat is equal to x sub ik beta hat k plus beta hat k, where x sub ik is the 1 by k minus 1 row vector with x sub ik drop. That's why you truncate also the beta hat vector. But then x sub k is equal to 1, so you would just have 1 times beta hat k. And if you do not have the treatment, then you would just have this first term. Okay. Then what is the average difference? Okay. So what is this? Y sub I hat, Y sub I 0 hat. This is just your, we have the expression for the expected value of Y given X. That is just your predicted X beta. Okay. So, so I'll just turn on my iPad so I can use my iPad. Mm-hmm. Hold on. Mm-hmm. Mm-hmm. Anyway, okay, so that W's are just your predicted X beta, X beta. Okay. Therefore, you would have, okay. So know that these are the predicted values at Y sub I, I'll stop share first so I can use my iPad. Okay. Okay, I'll go back to the screen share. Okay, so so these are just your predicted value of y given x. Okay, so this is for when x sub k is equal to 1. This is for x sub k is equal to 0. Okay, so if you look, oh no, this is, sorry, no, this is the predicted value for this is the predicted value for x beta hat. Okay. So that is x beta hat. Okay, and this is the expected value of y given x when x sub k is equal to 1. This is the expected value of y given x when x sub k is equal to 0 for the ith observation. Okay, so this is for x sub I. Okay, so when you get the sample averages of the difference, then you have the so-called average treatment effect. Okay, is that clear? Okay, so I think this is the first time we have the average treatment effect. Okay, is that clear?
Yes, ma'am.
Yes, po.
Okay. Okay, so usually you encounter those three terms: the partial effect at the average partial effect, and the average treatment effect when you go into project evaluation. Okay. Now, how can we measure the goodness of fit of the 2-bit model? Okay, so there are various ways of doing it. Okay, one is the simple squared correlation between the actual y sub I, which are 0 and positive values, and the predicted values of the model, okay, which is given here. Okay, so that is just consistent with the the usual interpretation of the R squared in our multiple linear regression model. The R square is just the squared of the correlation between the actual y's and the predicted y's. Okay. Or you can use the sum of squared residual type R squared comparable, which well, for the R square, you can express the R square if you look at the formula for multiple regression in terms of sum of squared residuals. Okay, so using this approach, the number you get would be comparable to the OLS R squared. Okay. Or you can use the predicted values given here to look at the fit for non-limit observations if you're concerned about particular observations. If comparing different models with full distributions specified, you can also use the log likelihood for the full sample. This measures the fit for the entire distribution. Okay, as always we prefer the model with the highest value of the log likelihood function. Okay. Okay, so that's the type 1 Tobit model. Now let's extend the Tobit model to the two-limit model. So now we allow for two limits. These might be logical or institutional constraints. Okay. Common corners are 0 and 1 or 0 and 100. Okay. For example, suppose workers are allowed to contribute at most 15% of their earnings um, to a tax deferred pension plan, and Y sub I is the percentage of income contributed for worker I, then the corners are at 0 and 15. I think like for the SSS, the private pension plan, um, beyond a certain level of income, there is a cap on how much you contribute to the Social Security Fund. Okay. So let us have the limits A1 and A2. A1 would be the lower limit, A2 would be the upper limit. Okay. Okay. So note that for these limits are not um they are not data problems, but um for this example, it's an institutional constraint. Okay. Okay. Let us define the two-limit Tobit model in terms of an underlying latent variable. Okay. So the latent variable is y star. It is what is linear in beta. So we have x beta plus u. Then we have the usual normality assumption for these disturbances. They're normal with mean zero and variance sigma square. Okay. This assumption will come up again when we go into the sensory data models. Okay. So we have the observed y's. Okay. So note that if y star is between the limits a1 and a2, then we observe y is equal to y star. However, if y star is less than the lower limit, then y is equal to a sub 1. If y star is greater than or equal to the upper limit, then we observe a sub 2. Okay. So note that the density of y is the same for y star if the values are between a sub 1 and a sub 2. Okay. Okay, so if y star is between a sub 1 and y sub 2, we actually observe y star that is y. Okay. Okay, so we would have, what is the distribution of y? The y would be normal with mean x beta and variance sigma square. So looking at this, so the since u given x is normal, then the the distribution of y would be the distribution of y star. So that would have mean x beta and variance sigma square. Okay. How about the endpoints? Okay. So as we have worked with the probit model and also the Tobit model, you would have the probability that y is equal to y sub 1 given x is the CDF evaluated at this. And at the upper limit, a sub 2, the probability is the CDF evaluated at this. Okay. So know that the CDFs have values between 0 and 1. Therefore, these probabilities would also be values between 0 and 1. Okay. So now we can write the log likelihood function. Okay. So the log likelihood function would be a function of the density of y sub I given x sub I and the parameter theta. Okay. Okay, so we would have so we have three cases: y sub I is equal to a sub 1, y um y is between a sub 1 and a sub 2, and when y is equal to a sub 2. Okay, note that the y's are observed values, so this should have a subscript. Okay. Okay, then since you have the log likelihood, then okay, for the first two, for the extreme points, a sub 1 and a sub 2, then you pick this up. And then for y between a sub 1 and a sub 2, then you take advantage of this normal distribution. Okay, you're working with the standard normal distribution. That's why you divide by sigma, but then you have this also. Okay. Okay, so this is the log likelihood. Then to get the log likelihood for the whole sample, then you just sum this L sub i's over all the observations I. Okay. So well-behaved and standard asymptotic theory for MLE applies. Okay. Then you can compute expectations to obtain magnitudes of effects. Okay. Let us look at the expectation conditional on not being a limit point. Okay. So that is if y is between a sub 1 and a sub 2, then this is the expected value. Okay. Okay. So note that this right-hand side is just an extension of the inverse Mills ratio. For okay, for the earlier inverse Mills ratio, um, we just have one term. Okay. But now when we have two limits, then we have two terms here in the numerator and the denominator. Okay, so that's the conditional expectation, assuming y is not a limit point. Okay. Now, what is the conditional expectation? Okay. Of course, if it is a limit point, the expected value would be either a sub 1 or a sub 2, right? Okay. So this is the formula for getting the unconditional expectation. So you have to take into account the three cases. Okay. So this is when you are at the lower limit. This is when um, the third term is if you're at the upper limit, and this is this. Okay, so you can fill in the probabilities, the probability that y is equal to y1, the probability that y is equal to y2. Okay, and you have, well, you had this, and then for the middle term here, then you have um, the probability that y is between a1 and weight a2. um, you That would be the normal. You take advantage of the normal distribution. Okay, so it would be this. And then you have the probability that y is between a1 and a2. Okay, so anyway, you can fill up these expressions from what we have found, what we have derived earlier. Okay, so for the partial effect of a continuous variable on the expected value of y sub y given x, then you get this expression. Okay. Okay, then you can, to get the partial effect at the average, then you just substitute x bar for x here. Okay. How about the estimated average partial effect for continuous variables? Then you have this expression. Okay. Note again, you have the scale factors, which are between 0 and 1. Okay. So that's the two limit Tobit model. So just work through it and try to understand how we get um, the estimation for the two limit Tobit model. We will go back to this two limit Tobit model in an application of the sensor data, one of the sensor data models. Okay. Any questions?
Ma'am,
Okay.
question, ma'am.
Yeah, sure.
For determining if a particular population regression model is has is appropriately corner solution responses. Do we look at how if it how can we say if it's a corner solution response? Because I
Okay.
think I've read somewhere that it it could mean that there's missing data um or it depends.
Okay.
It's not
We'll be going to censored data. So you would see at least some case when you can distinguish between a Tobit model where the zeros are results of behavioral um, outcomes, um, as distinguished from zeros that are due to uh, some that are due more in the way the data was collected. It was a data problem, not really uh, arising from the behavior of the economic agent. Okay. Well, in sensor data, that is the kind of problem we address. Okay. Okay. So I'll shift to sensor data. Oops. Hmm. Wait, I have to. Wait, I have to. Mm, okay. Okay, so we move to sensor data. Okay. We'll be covering binary sensoring, where we end up using again the probit model. We will have interval coding, where we would get interval regression, and we will have sensoring from above and below. Here we will encounter um, the sensor normal regression. Okay. Okay, so what is the problem we consider now? We now consider estimation of standard population models where the response variable has been censored in some way. Okay, so this is more of um, due to the treatment, the way the data was collected, or um, or gathered. Okay, we obtain a random sample of units from the population, but we do not observe the entire range of the dependent variables because the data has been censored in some way. Okay, some estimation methods are similar to those we have covered, like the probit and also the tobit. However, they are used to correct missing data problems and not to obtain better functional forms. Okay. Therefore, we now refer to data censoring as distinct from, say, corner solution responses, where we apply the Tobit model. While data censoring produces a pileup at certain values, it is not for behavioral reasons. It is just a rule about how the data are collected. Okay. Okay. So the problem you address with Probit, Logit, the multinomial response models, and Tobit are different from the problem we are addressing with data censoring. Okay. Okay, so let's start with the simplest model uh, to illustrate the censoring problem. Okay. Okay. So the simplest model is that of binary censoring. So again, just like in the Provit model, we observe 0 or 1 for the left-hand side variable. Okay. Binary censoring is an extreme form of data censoring. Let us start with the standard linear model for the population. So we still assume that um, we have the standard linear model for the population. Okay. This is our okay, this is our standard linear model. Okay, we do not even have normality here in this um, in this model. Okay, all that we're assuming is that we have a linear model. We will assume random sampling. There's no multicollinearity. There's no perfect multicollinearity, and we're assuming that X is exogenous. Okay, that's all we're assuming here. We're not assuming normality. So X here is K by 1, is 1 by K. X is a row vector. Therefore, this beta is K by 1 vector. Okay. Um, with the model having an intercept. So x of 1 is equal to 1. Okay. The variable y may be willingness to pay for a proposed public project. So say y is equal to WTP, willingness to pay. When we draw, say, family I from the population or household I from the population, we'd like to observe X of I. Usually this would be socio-economic characteristics of the family or the household and the household's willingness to pay for the project. If we did for all I, we would estimate beta by OLS. That is, if we can collect data on this WTP. Okay. And of interest primarily to us is beta, which contains the partial effects of interest. Okay, beta gives us the partial effects of this x of i's. Okay. Okay, but in the real world, willingness to pay can be difficult to elicit, and reported amounts might be noisy. Instead, suppose that each family is presented with the cost of the project R sub I. R sub I can vary across households. Okay, it need not be the same for all households. Okay, so it could be that if you are if it is an irrigation project, probably if you're quite far from where the water supply is, or the pressure or the amount of water that reaches you is less than, you might be given a lower R sub I. Okay, if the benefits are perceived lower um, for you. Okay. Anyway, the point is that R sub I can vary across households also. Okay, then the household either says it is in favor of the project or not. Okay, so we have an indicator function, um, w sub I. W sub I is either 1 or 0. It is 1 if his willingness to pay is greater than R sub I, and his willingness to pay, and what W sub I would be 0 if his willingness to pay is less than R sub I. Let us assume that the chance, this is not, that the chance that Y sub I equals R sub I is 0. Okay, just to make it simple. Okay. Okay, so we do not observe Y, the actual willingness to pay, but what we observe would be W sub I's. W sub I can be 1 or 0, and that's a result of this indicator function, whether his willingness to pay is higher or lower than the cost of the project R sub I presented to family I. Okay. But what are we interested in? We're interested in, going back to our original model, we're interested in the expected value of y given x. Okay. So that is the expected value of the WTP given x. Okay. And from our model, that is equal to x beta, since the expected value of u given x is 0. Okay. Okay, so that's why we would like to estimate beta. Okay. But beta cannot be estimated by OLS because WTP cannot be observed. Okay. So let us impose some strong assumptions on the underlying population and the nature of R sub I, so we can proceed with maximum likelihood. Okay. Okay, so first, let us assume that the conditional distribution of the disturbances given x sub I, R sub I is normal with mean 0 and variance sigma square. Just like in the Tobit model, except that now we have this R sub I also. Okay. So the underlying population model satisfies the classical linear model assumptions, okay, where we have the normality assumption. Okay. Assume that for a random draw, R sub I is independent of Y sub I conditional on X sub I. Okay. So we assume that R sub I, the project cost offered to the household, is independent of his willingness to pay. Okay. So it's not like if you're the one undertaking the survey, you would say, oh, this household is likely going to bid low, so I will lower R sub I, the project cost presented to him. Okay. So this assumption rules this out. And mathematically, we say the conditional distribution of Y sub I given Xi R sub I is equal to the conditional distribution of Y sub I given X sub I. Okay. So this says that Y sub I and R sub I are independent. Okay. Okay. This notation denotes conditional distribution. Okay. We will we will be using that notation quite often with these sensor data models. Okay. So just to repeat, the above assumption says that Y sub I and R sub I are independent, conditional on the vector X sub I. This conditional independence assumption is satisfied if R sub I is randomized, set independently of X sub I, Y sub I, or if R sub I is chosen as a function of X sub I or conditional on X sub I, R sub I is randomized. Okay. So we impose the condition that R sub I is independent of Y sub I, which is the willingness to pay. Okay. Let us derive the expression for what is the probability that W sub I is equal to 1, the indicator function is equal to 1 given X sub I, R sub I. Okay. Okay. So X sub I, R sub I would be appearing on our right hand side. So that's why we are conditioning on X sub I, R sub I. Okay. But when is W sub I equal to 1, W sub I is equal to 1 if the household's willingness to pay is greater than R sub I. Okay. Okay, then, well, in the next line, I just subtract X sub I beta to both sides of the inequality here. But then Y sub I minus X sub I beta is just U sub I. Okay, using our model. Okay. And then, but then we have information about the distribution of U sub I. We want to work with the standard normal distribution. So we divide by sigma. Okay. Okay, then the complement of this event is just this. So the probability of this is 1 minus the probability of this. Okay. But if you look at this expression, we know that U sub I over sigma is normally distributed with mean 0 and variance 1. Okay, so that is just, this expression is just the CDF evaluated at Ri minus Xi beta over sigma. Okay, so we have brought in the um, conditioning variables X sub I and R sub I. Okay. Okay. But then by symmetry, this expression is equal to the CDF evaluated at Xi beta minus Ri over sigma. So I just have reversed this one. So I just get the minus of this. Okay. That's why I have X sub I beta minus R sub 1, R minus R sub I in the numerator. Okay. So if you expand this argument out, so that is the CDF evaluated at, okay, so you have beta 1 over sigma, um, beta 1 over sigma, why do I have A? No, I should have no A. Okay, I have beta 1 over sigma, okay, and then so that takes care of the intercept. I have x here would be equal to 1 plus beta 2 over sigma x sub I2 plus beta 3 over sigma x sub I3 and so on to beta k over sigma x sub ik. But you have this minus ri over sigma. Okay. So this expression in brackets is just this. Okay. Okay. So what do we observe? Okay. We observe x sub I for WTP studies is usually socioeconomic characteristics. We have R sub I, the project cost offered to the or presented to the household, and W sub I would be a binary variable, 1 or 0, depending on whether his willingness to pay is higher than R sub I. Okay. Um, Note that willingness to pay WTP is not observable. Okay, but implicitly household or the household or the person you're interviewing has an feeling of what his willingness to pay is, but really cannot just give an exact amount. Okay, since we observe this data for random draws from the population, then how do we estimate the model? Then we can do probit W sub I on X sub I and R sub I. So we do probit. On the left hand side, we have W sub I 0 ones. And on the right hand side, we have X sub I, R sub I. And that would consistently estimate beta over sigma as the vector of coefficients of the X sub I's. Okay. Okay, so beta over sigma would give you the coefficients of X sub I. Then you have minus 1 over sigma for the coefficient of R sub I. Okay. Okay. So here, you for probit, you would be estimating the betas and also sigma. Okay. In almost all applications, X sub I would include an intercept, and we assume it here. Okay. Okay. So what we get are estimates of beta and sigma. Okay, so let gamma be beta over sigma. Okay, beta over sigma, let that be gamma, and let alpha be minus 1 over theta, the coefficient of R sub I. Okay. Okay, note that probit will give you estimates of gamma hat and will give you estimates of gamma and alpha. Okay, so this would be what would be estimated by probit. So you have gamma hat and alpha hat. Okay, but of interest are the betas. Okay, okay. So from this equation, we have beta is equal to sigma gamma. Okay, so if we're looking at the Jth coefficient, we get this. Okay, but what is the estimate for sigma hat? Okay, so from here, you get sigma is equal to 1 over alpha, right? Minus. So sigma hat would be minus 1 over alpha hat. Okay, this maximum likelihood estimation. So just substituting the so you can safely do this for maximum likelihood estimation. Okay, because the is the way you do the prelims. Okay, therefore, what is gamma hat here? Gamma hat is minus 1 over alpha hat. Therefore, beta hat is minus gamma hat j over alpha hat. Okay. Yeah. When we started off, we said that what we're interested in is the beta here. Okay. But then probit would give you estimators for these coefficients. Okay, so we have to do this transformation to get beta hat j's. Okay, so standard errors can be obtained. Standard errors for the beta hat j can be obtained by the delta method or bootstrapping method. Okay, just read up on this in Woolridge book. Okay, just look at the sections. You do not have to memorize how it's done. You just need to have a feel of how they do the delta method and the bootstrapping. Okay, so these are just iterative methods when you do not have an explicit formula for the variances. Okay, then some notes on the binary response. What if the linear model for WTP is unrealistic? Suppose we could observe actual willingness to pay. We would most likely observe WTP would be greater than or equal to 0, with WTP equal to 0 for some fraction of the population. That is, they would not want to pay for the project. What if the population model is Tobit? And this is the Tobit model, right? Okay, note that if we have binary censoring with R sub I is greater than 0, that is the project cost offered is always positive for all I, the estimation procedure is identical to that outlined for the linear model for what we had here. Because we do not observe y sub I, we cannot distinguish between a linear model and a two-bit model when all r sub I is greater than or equal to 0. Okay. Nevertheless, if we believe that y is a 0 for non-trivial fraction of the population, any calculation should then reflect the type 1 Tobit formulas for estimating the partial effects. If you believe that the zeros are actually zeros, then use Tobit. Okay. If y sub I is always greater than 0, that is willingness to pay is always positive. You do not have zeros or corner solutions. A better model would be of this form. So this ensures that y is positive. So you have exp x beta plus u. Okay. And alternatively, this is the same model as log of y is equal to x beta plus u. Okay. So really, these are not two alternative models. They just say the same thing because the logarithmic function is just a positively monotonic transformation of this, right? Now you can apply the previous analysis with log of Ri, replacing Ri, assuming R sub I is greater than 0, okay? Okay, so assuming that the project cost offered is greater than 0, okay? So the probability that y sub I is equal to 1 given x sub I, r sub I would be the CDF evaluated at x sub I beta minus log of r sub I over sigma. So it is the same. Our earlier model is y sub y is equal to x beta plus u, okay? Okay, so if the correct model is y is equal to x sub I beta plus u, our original model, then this is the probability that w sub I is equal to 1. If the correct model is this one, then you would have the probability that w sub I given 1 is equal to this. So note between these two, so just compare these two, okay? So between those two, the only difference is in this term, okay? Okay, so well, for the original model, you do probit w sub I on x sub I, r sub I, right? For the second model, you do probit w sub I on x sub I log of r sub I. Okay. So how would you choose which is the better model? Then you can just compare the log likelihoods, okay? And indirectly, then you would be answering the question, um, is it better using r sub I or log of r sub I? You would like to the one that produces the larger value for the log likelihood function. Okay. Note that the log likelihood function can also be negative, which is fine. Okay. Because you know that if the argument is between 0 and 1, the log likelihood would be negative. Okay. Any questions on the binary response model? Okay. So this is an extreme kind of data censoring. Okay. it brings you back to the probit model where the left hand side is just um, binary. W sub I is 0 or 1. Okay. However, here, what would be churned out would be estimates of these um, parameters. Okay. Then you have to recover estimates of the beta J hats. Okay. And that is what is of interest to you because because of your underlying your hypothesized underlying population model, which is this. Okay. So the beta hat J, then you that would have the usual interpretation, the partial effect of Y, the partial effect of the expected value of Y given X of J. Now let's move on to interval coding. I'll just introduce it since it's 2/4. Okay, so this is now um, um, more general because we now have intervals. It's not just 0, 1. Okay, we now consider we still consider the standard linear model. So the underlying population regression model gives us the expected value of Y given X is equal to X beta. Okay, where the response variable is recorded as falling into certain intervals. However, the underlying variable Y is still we still assume to be continuous. Okay, so the underlying variable Y is continuous, but Y is not recorded. What is recorded would be how those fall into how those Y's fall into intervals. Okay, so we have so-called interval coded data or interval censored data. Okay, so let R sub 1, R sub 2 down to R sub j denote the known interval limits. These are specified as part of the survey design. For example, rather than asking individuals to report actual annual income, they report the interval that their income falls into. Okay, so you often see that in household surveys. You don't, sometimes you do not get the actual annual income, but individuals are asked to check into which income interval they fall into. Okay. However, there is um, a lower limit and an upper limit. So if your income is below R sub 1, your you're recorded in the first interval. If your income is greater than R sub j, you're recorded in the last interval. Okay. Okay. Under the classical linear model assumptions for y, that is now we put the normality assumption, the conditional distribution of u given x is normal with mean 0 and variance sigma square. We can estimate beta and sigma square by maximum likelihood estimation. Okay. Now the structure of the problem is similar to the ordered probit model, but there would be some differences, okay, which we'll go into later. Okay. So define in the population an ordered variable W. Okay. So W would be 0, 1, down to J. Okay. So for example, if your income is less than or equal to R sub 1, W is equal to 0. Okay. Then if your income is between R sub 1 and R sub 2, you earn 2 W sub 1, and so on. If your income is greater than R sub j, then you are in the interval j. Okay. Okay. Now the probability that W is equal to J for J going from 0, 1 down to big J have the same form as the ordered probit. Okay. So so if you look at your notes for ordered probit, for a random draw I, the likelihood is given here. Okay. An observation I would only fall into one of these categories. Okay. Okay. So it would just have one term picked up, one term in the from the right hand side picked up for the log likelihood for observation I. Okay. So here you have the CDFs again. Okay. So you can just work through that. Okay. However, if you look back at your ordered probit model, the sigma here would be equal to 1 for the ordered probit. That's why you don't have sigmas for the ordered probit. Okay, if you look at the assumptions for the ordered probit model. Okay, then solving the maximization problem, you maximize the sum of the likelihoods, um, sum over all observations, I going from 1 to 10. So note that you are maximizing with respect to beta and sigma. You want to find the maximum likelihood estimators of beta and sigma. Okay, so those beta, you want estimators for this beta given here, or y is equal to x beta plus u, you want the estimator for that beta. And sigma square is the variance of u given x. Okay. 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 So the maximum likelihood estimators, beta hat and sigma hat square, are often called interval regression estimators. So these are the interval regression estimators with the assumption that the underlying population distribution is homoscedastic normal. Okay. So for theta, you have the command interreg for interval regression. So that would give you estimators for beta hat and sigma hat square. Okay. Okay, so the command is different from probit or ordered probit. Um, Using the robust option with the MLE estimation is an admission for these limited dependent variable models that the underlying population model is incorrect. Okay, so usually it does not work too well for these models. Inference is robust. However, the inference is on the wrong parameters because if your underlying population model is misspecified or incorrect, you should then correct that model, and that correction would give you the correct parameters to estimate. And your estimation procedure should be dictated by those parameters, those, yeah, those parameters. Okay, so these are differences between the interval regression and ordered probit. In ordered probit, we are interested in a discrete response variable, which is something like a credit rating. As we said, only ordinal ranking matters, okay? That is for the ordered probit, okay? However, in interval regression, We are interested in the underlying continuous variable y, which has quantitative meaning. Though we're working data-wise using intervals, the underlying variable is continuous, and that has quantitative meaning. Okay. Secondly, in ordered probit, the cut points are parameters to estimate, while for ordered probit, um, the interval limits are given, and the parameters beta do not completely measure the partial effects. We said that we have those those scaling factors between 0 and 1. Okay. In interval regression, the interval endpoints are given or are themselves data, and beta contains the partial effects of interest. As in the case of binary censoring, when we obtain interval regression estimates, we interpret beta hat as if we had been able to run the regression y sub I on x sub I going from 1 to n. Okay, so note that this maximum likelihood estimation gives you directly estimates for beta, and you can interpret those beta as giving the partial effects of say x sub j on the expected value of on this expected value. Okay, so the interpretation is more direct. Okay, in interval regression, the interval endpoints are given or are themselves data, and beta contains, okay, so imposing the assumptions of the classical linear model, that is where we have the normality assumption, allows us to estimate the parameters in the distribution of the conditional distribution of y given x, even though the data are interval censored. And that's why we need the classical linear model where we have the normality assumption, so we can do the maximum likelihood estimation. Okay, here. Note that we have the CDF and the density function of the normal distribution. Okay, so I'll stop here, and next meeting, um, tomorrow, go to censoring from above and below, and then take also, then after that, we'll go into sample selection. Okay, okay, any questions? Do you have questions? So I'll see you tomorrow, 10 o'clock. Okay. So we'll finish censoring from above and below, and then move to sample selection, which is an interesting problem also in economics. Okay. Okay, so see you tomorrow.
Thank you po.
Okay.